This is Abrara Rome. Today I will present our paper supporting home quarantine with smart speakers. This is a joint project with my advisor, Dr. Chiu Tan. So first I will give a high-level overview of home quarantine monitoring. Then I will present some challenging of using smart speaker for home quarantine monitoring. After that, I will propose our solution, then the result, finally conclusion and future work. So the outbreak of COVID-19 has been led many countries to ask their citizens to home quarantine or shelter in place order to reduce the spread of the virus by limiting contact with individuals outside the household. So this table shows an example of these rules. So for example, in New York City, on March 23rd, all people stay at home, only leave their home for essential stuff. While in Saudi Arabia, on March 8th, all people stay at home, free to leave their home to gather essential supplies. But on March 23rd, they announced a national curfew. Only one person can leave the home for essential stuff and between 6 a.m. to 3 p.m. only. So consequently, quarantine monitoring techniques have been proposed to measure a commitment to this order. So this involves some tracking of mobile phone or other wearable devices. Amazon Echo and Google Home are most used smart speaker. Some studies show that 10% of the world consumer own smart speaker. And according to recent survey, over 50 million Amazon Echo devices have been sold in US alone. So smart speaker is always on device that is constantly listening for the keyword wake up, for such as Alexa or Hey Google, to be activated. So we can make use of this constantly listening behavior to monitor voice in the home so as to determine whether the family is maintaining a quarantine or not. So for example, a home with visitor will include voices that are not supposed to be there. So challenging. Using smart speaker to monitor voice in the home is a challenging problem. So first, we want to protect the privacy by avoiding sending the audio recording to the backend cloud for processing. Second, a home has many sources of interference that will distort simple voice counting. So for example, characters talking on the television may be mistakenly be considered to be a visitor based on the voice alone. So our solution, we propose monitoring solution to count the number of occupants in the home while addressing two main aspects. First, our technique is sufficiently lightweight that avoid using back-end cloud computing to protect the privacy. Also, it's robust against common background noises such as television. So current work looks at one component of the quarantine monitoring system of how use voice to estimate the number of people in the home. So this component is useful in the common case where home occupants talk freely between themselves. Ongoing work, a home quarantine monitoring system will need to address several conditions, including when the home occupant intentionally attempt to evade the detection. So for instance, a smart speaker will obviously not detect any voice if the visitor keeps silent all the time. So counting voice with a smart speaker has three main components: lightweight audio processing, eliminating distortion from the media, and counting unique individuals. We will discuss each one of the components in more details. So first, the lightweight audio processing. So a lightweight privacy perceiving method using a Gaussian mixer model that run on the device itself without the need to send to the backend server. So our strategy uses a passive monitoring and active verification. The monitoring algorithm will continuously listen, but will not transmit the data to the backend server. Only transmit a comment when the local monitoring algorithm detects that someone is not at home. So existing smart speaker architectures require the device to be always recording to listen to trigger words, after which the following few seconds of the audio recorded and sent over the internet to cloud server, where machine learning and natural language processing algorithms are used to parse the recording into understandable commands. While these algorithms are powerful, they do require the processing capabilities of a cloud server. This creates a privacy risk when used in monitoring a family, because we will need to send a large amount of audio recording to the cloud server for analysis instead of just a few sentences. So this figure shows the overview of audio processing. So the analysis of the family quarantine commitment is based on the sound recorded by smart speakers. We refer to these recorded sound as audio snippets. So the objective here is to characterize an audio snippet into one of the three categories: live speech, which is defined as one or more live people talking; media, which could include speech or music from non-live source like a television or radio; and finally, uncategorized, which is the absence of both the media and live speech. So the rationale behind classifying audio snippets into these categories is that the live speech segment can later be used to infer the family quarantine commitment. The media segment has sound from television or radio, which may confused with the live interaction in the family and need to be filtered out. So the second component is eliminating distortion from the media. So the filtering algorithm addresses the media background noise interference in the home environment. So this algorithm provides a robust approach that able to differentiate between live speech and non-live speech, and later filter out the non-live speech, such as the media or unvoiced, such background noises. So in order to distinguish between media and other categories, we first divided audio snippet into n shorter overlapping segments of equal length. We then classify each snippet using two features: the pitch and MFCC feature. So the pitch is fundamental frequency of speech sound and is directly depends on the vocal fold. We use the pitch value to distinguish between speech and non-speech sound, since the most distinctive trait between different voice is their fundamental. So figures here show the pitch fundamental frequency over the time for two audio signals. The dotted blue line corresponds to recording of live speech speaker, and the full orange line corresponds to the recording of the same live speech speaker after playing it back on the TV. So we can see when we play the same live speech on television and record it again, it tends to have higher of vibration per second, more frequency component, and lower volume compared to live speakers. While the MFCC is used to compare the similarity between segments, since it is distinctly characterize each voice. We extracted 20-dimension MFCC feature from 32 millisecond frame with 50% overlap. Then each segment classified into one of the three classes using Gaussian mixture model. The GMM model, trained with a standard expectation maximization algorithm to estimate the parameter that maximize the likelihood of the model. Then later, the live speech segment, along with the feature vector, saved for further analysis to count unique individuals. The MFCC used to compare live speech segments together to see if it's belong to the same source or not. The last component is counting unique individual. So we have multiple members in the home, and we want to segregate their voice easily and lightweight by identifying who is speaking without prior training of the family member's voice to be applied to in the wild for any family. So this figure shows the process of speaker segregation. Each speaker will have one list containing all the segments where the speaker's voice appear in the audio snippet. So this is done by comparing the MFCC vector of the segment that labeled as live speech with the MFCC in each list to investigate whether the two live speech segments are belong to the same participant. Then group the similar segment into the same list. The similarity distance between the pair of MFCC vectors calculated using cosine similarity. So the advantage of our segregation approach is that it's better to protect privacy than the voice recognition approach, and also opposed to distortion caused by television. So we evaluate the performance of our technique by performing experiment or real-world traces recorded from 5 different families. So the media data set collected of audio recording of 2 live people talking while different television shows are playing in the background. We have 5 different types of the shows: movies, news, cartoons, sport, and talk show. The multi-family data set collected from 5 different families during family time. We recorded 1 hour from 3 different days, 2 weekdays, and 1 weekend. Evaluation metrics. So the accuracy of number of speakers measure depends on the accurately distinguish between live speech and non-live speech while counting the number of voice. Therefore, we use error percentage matrix to measure the accuracy of counting. We also evaluate the reliability of media filtering approach on realistic scenario when it's interfere with conversation. So we use a false positive rate and false negative rate to evaluate the accuracy of detecting media filtering algorithm in the wild. So false positive rate is percentage of non-TV segment that predicted as a TV, while false negative rate is the percentage of TV segment that predicted as non-TV. As a result, Figure 1, we compare the performance of our algorithm with existing literature counting algorithm called Crowd++ using the media datasets. So the average error percentage for Crowd++ is 23, while our approach is 4. So compared with the ground truth, which is to live speech speaker, the Crowd++ yield to some overcounting of the number of live speech with talk show, news, movies, and some snippet of the sport. However, our filtering algorithm is able to distinguish between a live and non-live, and then further eliminate them from counting algorithm. Therefore, our technique is robust against common background noises. We can observe from figure 2 that the media filtering algorithm achieve an overall accuracy of 92%, false positive rate of 8.8%, and false negative rate of 7.4%, with the highest accuracy being 100 for family 2, lowest being 86 for family 4. This result proves that the media filtering algorithm is reliable. That means it does not filter out an important segment which may affect the accuracy of counting. Finally, figure 3 shows that the overall error percentage for estimating the number of participants for each family during the family time. The speaker segregation algorithm achieved overall average error of 5.9%. So, in conclusion, we present a solution that used smart speaker to count the number of occupants in a home that help in monitoring commitment to quarantine rules. It is sufficiently lightweight to avoid using back-end cloud computing to protect the privacy. It's robust against background noises. Ongoing work is to incorporate our counting technique into complete home monitoring system that also consider a home occupant trying to break the quarantine without being detected. Thank you for listening.